All right, let's get started. This is our second lecture, and today we're going to talk about asymptotic notation. This is something I alluded to in the end of last lecture when I write something T of n equals theta in. This is asymptotic notation. So today we'll talk about what it means and how to use it. And this is going to be big basis for your homework, which is going to be out later today. So, when we talk about running time, we could try to write out that the number of steps by the algorithm is something like this. Give a lot of detail. And I think we touched upon last time what's the problem with doing this. So one of the things is hardware changes, the number of actual steps changes. So we don't really want this kind of derivation to depend on the specifics of the hardware you use. The second, it's just exhausting to analyze an algorithm to this level of detail, right? We also want to make it easy on ourselves and not have to count every single little step. And finally, ultimately, we want to compare running times of algorithms. So we want to kind of group them together into categories that have similar scaling properties. This is really what we were after. We're after not exactly how many steps an algorithm takes. What we're after is how that number of steps scales with the input size. In other words, if I double the input size, what happens to my running time? And like this kind of level of detail really obscures that. It really kind of hides the forest when you're down looking at the trees. Okay, so instead, we want to capture order of magnitude kind of, or of the growth of the function of T of n. Okay. And we want to be able to then compare using this notation of big O and similar things. So in particular, we're going to have big O, big omega, theta, and little o. And the way we think of this, the way you should think of it intuitively, is that big O is kind of like less than or equal to, big omega is kind of like greater than or equal to, theta is kind of like equal to, and big O is kind of like smaller than, strictly small. We'll give the precise definition, in this lecture, but this is kind of what I want to have you thinking in mind to have the intuition for what we're doing. So again, what do I mean by order of magnitude of growth? If I just make a simple table with one column being n, and try n4, 8, 16, so I'm doubling here every row, doubling the input size of the previous row. Now, if I put here n squared as another column, then this would be 16, 64, and 256. So as I'm doubling each row, in input size, the number of the function quadruples. So each of this is a multiple of 4. And if I write 2 to the n, then this would be 16, 256. This is actually, I have my notes, 65,536. So here, when I double n, I actually multiply I actually square or multiply this number of steps. I multiply by itself, so I square it. In other words, when I double the input size, I square, so 16 squares, 256. I square the running time if it's 2 to the n. I double the input size, I square the running time here. So that's pretty bad, right? Pretty bad scaling. On the other hand, if I put log n here, I'm going to use base 2. Then this would be 2, 3, and this, the log base 2 of 16 is 4. So here with the log, as I'm doubling the input size, I'm just adding 1, to the runtime. So this is really nice scaling for running time. I want to show you some real numbers from another textbook. So here, there are different values of n, 10, 30, all the way to 1,000,000. And here there are more functions that are being shown. So from n log n squared, n cubed, 1.5 to the n, 2 to the n, and n factorial. And what this is showing is giving a typical processor, if you were to run this many instructions, this many, like n squared instructions with this value of n, this is how long it would take. So one thing you really kind of notice is that if you look at a single row, like look at the last row, there's a big jump. There's a point where there's a big jump. So, 1 second, 20 second, reasonable, all of a sudden 12 days, and then all of a sudden 31,000 years. And I think very long, it's more than 10 to the power of 25 years. Pretty long. And like if you look at n equals 100, you see less than a second, less than a second, less than a second, all of a sudden 12,000 years. And this is really the intuition behind thinking about the running time, not in terms of precise formula for the number of steps, but in terms of these categories, these buckets of n squared, n cubed, 1.5 to the n, so on. Because you see there's such a big difference in terms of scale, in terms of what you can run. For each one of them, like for 2 to the n, there's a point where things become unreasonable. So here, when you go from 30 to 50, you go from some reasonable running time to unreasonable. For n cubed, depending on what you define, but like for maybe between 10,000 to 10 million, you go from some potentially reasonable running time to something not reasonable. So there's always this kind of breaking point. And that's why it's important to know this, to kind of think of the running times in terms of these classes. So we would like now a theoretical framework to separate these classes, and that's what this big O notation is going to let us do. Now let me give you definition, big O. So the definition is function f of n is big O of another function g of n. So we write f equal to O of g, or we write f of n is equal to big O of g of n. Or we sometimes abuse notation, right? F belongs to the class of functions O of g. F of n belongs to big O of g of n. The reason for this notation is kind of irrelevant for the purposes of this class, and I'll try to use the equal sign wherever, but if you see me kind of slip through and write this kind of notation, you'll know what it means. So a function f of n is big O of g of n if and only if, to write IFF, there exist constants c greater than 0 and n not greater than 0, well, yeah, greater than 0, such that f of n is less than or equal to c times g of n for all n greater than or equal to n naught. Okay, that's the definition of big O. So this, by the way, definition is slightly different from the one you have in your textbook. And they're actually equivalent definitions, but we won't get into proving that. In fact, we in class will go into more detail than your textbook goes into. So let's do as a warm-up to understand this definition, an example. To show that n claim n is equal to big O n squared. Okay, so here, to apply a definition, we need to write, well, let's do proof of the claim. So we set f of n equal to the first function and g of n to be the second function. Now, need to find c and n naught such that, so what we have f of n has to be, right, f of n has to be less than this. So we need, now plugging in what those are, n less than or equal to c, g of n is n squared, for all n greater than or equal to n naught. Well, so n squared is actually greater than or equal to n for all n greater than 1. So if we set c equals to 1 and not equal to 1, then we have n less than or equal to n squared for all n greater than or equal to 1 is true. That proves that n is big O of n squared. So what I mentioned is that that big O is like a less than or equal to, and so in some sense, in an asymptotic sense, n is less than or equal to n squared. And you can see here kind of that's kind of what it's saying. But there are two ways in which it's different than just saying it's less than or equal to. So the first is you're allowed to be off by some constant factor. So you're allowed to scale your function g of n to make it bigger. I'll show you an example in a second. The other thing is you only need this to hold. You only need g to be greater than f for big enough values of n. So like for small values, the functions are allowed to do whatever they want to do, as long as there comes a point, and 0, and not, I should say, when after that, this thing holds. So those are the two main ways in which big O is different than just saying less than or equal. Let's do a couple of examples to illustrate that point. So here's a claim, 6n is, see, I already made the mistake, here, equal to O of n squared, O of n. Proof. Right, so here you can already see that 6n is not less than or equal to n. Right, so here we're going to be using one of these differences. Particularly, we're going to be, in order to prove this, we're going to need to have this factor of c to scale the right size so it is bigger than 6n. So here, f of n equals to 6n, g of n equals to n squared, and need to find c and n0 such that, now plugging things in, 6n is less than c times n squared for all n greater or equal to n0. Yes. I did. Thank you. That was same. Okay. I know when I got more than one question at the same time, then I probably miswrote something. So it helps now to just to picture these guys. So what is the function f of n look like? 6n, right? It's some steep curve like this. It's a line, right? And it's a slope is 6. And the other is n, slope is 1. So n here is below 6n, but if you multiply it, so if you multiply it by 6 or by 7 or by 8, then this line can now become higher than this. And that's what this big O notation lets you do. So we're going to set, we need C to be anything at least 6. It could be anything, but the obvious thing to put is 6. And notice we don't, the n naught, we can just default it to 1. So just start from the beginning. Now, why 1? Why not 0? Well, these functions, remember what they're representing. They're representing running time, number of steps. These are as a function of input size. So we're really only interested in these functions when n is at least 1. So that's why we will set n not to be 1 to start, like as a default, unless we need something more. So, okay, so we set this, and then we would get 6n less than or equal to cn for all n greater than 1. And that's true. Oh, sorry, yeah. So the C becomes a 6. So yeah, this statement is now truly true, and we proved this theorem. Let's do another example to show you the role of n naught. So claim 6n is equal to O of n squared. Proof. So here, f of n equals 6n, g of n equals to n squared and need to find c and n naught such that 6n is less than or equal to cn squared for all n greater than or equal to n naught. Now, how does this function, how do these functions look like? Well, 6n is our line, and n squared, remember n squared is a parabola, it's n squared. And then put it squared. Now you guys know a parabola goes up while a line keeps on going. So the parabola will, even though it's smaller than 6n, eventually it will overtake 6n. And this is what I meant, that in this initial portion, we're allowed to like not care whatever happens here. We just want, after a certain point, that n squared is bigger than 6n. All we have to do is find, what is this point? What is this point? We'll make it n naught. So find n naught such that those two things are equal to each other. So 6n naught equals to n naught squared. So when this is equality, n naught equals to 6. So at n naught equals 6, now n squared is bigger than 6n. So we set n naught equals to 6. And in this case, we don't need to make use of c. We just set it to 1. Then we have that 6n is less than or equal to n squared for all n greater than or equal to 6. And this is true. Right, because why? Because 6n less than or equal to n squared, divide both sides by n. This is 6 is less than or equal to n, and this is true when n is more than 6. Why? Any questions? That's the definition of big O. Now, we have these other guys, omega, theta, and little o. So let's define omega. Now, we're going to define, yeah, question. Yeah, good. So the question is there an example where we need both C and not to be something non-trivial? Actually, not really. You can always use one or the other. So the answer is, I'll give you like, I'll explain using this example. It's a good question. So in this example, I worked by setting n naught equals 6. I could have also scaled n squared, so make n squared to be like 6n squared. And then that parabola would have actually gone sharply up right away. Right? So that way I could have used C instead of n naught. And that's why we don't, so the definition of the book, I think only uses C. Doesn't have n naught, and that's why. Because you can always get by with just C and not n naught. But let me rewind that, for the rest of the class, it's easier, I think, to think about this the way I described with C and not. And so, you should feel comfortable using, basically trying to think of how the plot looks like and deciding whether you need to scale it up, like here, or there's this kind of crossing point that you need to find. So how do we define big omega? So let's go back to the intuition of greater or equal to. So remember, it's like this. If we're talking about just regular numbers, I can say A is greater or equal to B if and only if B is less than or equal to A. Right? We all agree on this. It's so trivial you probably don't even think about it, but you can, if no one knew what the definition of this symbol was, you could define it in terms of this symbol. And that's exactly what we're going to do with big omega. So definition, F is equal to big omega of G if and only if G is equal to big O of F. For example, to show n squared is omega of n, you need to show instead that n is big O of n squared, which we just did. So I won't talk a lot about big omega because it's basically whatever you know about big O, you can use to prove something is big omega. The other thing is I want to talk about theta, which is kind of like equality. So equality, how would you define A equals to B? Well, you can define it as A equals to B if and only if A is less than or equal to B and B is less than, and B, and A is greater than or equal to B. That's one way to define equality with real numbers. I mean, with just regular numbers. So we do the same thing here. So the definition, F is theta of G if and only if F is big O of G and F is omega of G. Equivalently, F equals to theta of G if and only if F is big O of G and G is big O of F. So we just applied the definition of omega to convert this to this. Both are equivalent. Now, there's another way, it's maybe easier for many people, way to prove that these relationships instead of applying the definition. So that is using limits. We have the following property. If the limit as n goes to infinity of f of n over g of n exists, then if this limit is not equal to infinity, then f is big O of g. And if this limit is positive, strictly positive, then f is theta of g. Okay, so for example, we showed that 6n is big O of n. We showed it directly from the definition of big O, but we can also do this limit of 6n over n, which is limit 6, which is 6, which falls into both of these categories. So it's both of these categories. We already saw that it's big O of g. Turns out it's also theta of g. So theta of g, y. Let's rewind. Theta of g would be to show that 6n is O of n and 6n is omega n. That's what theta means. So let's see. I mean, we know from the property, we know that this has to be true, but let's see if we can prove it from the definition of omega. So this equivalently is that n is big O of 6n. And this show by setting, now I'm going to be doing this one on the fly because it's really easy. You set c equals 1 and n not equals 1 because n is less than or equal to 6n for all n greater than 1. Right, so you don't, I mean, here n is really less than 6n. We don't need to scale it. We don't need to say for big enough n is just true. So this is an easy one. But you could have avoided doing all this looking for c and n just by looking at this limit. Now, you won't always find this limit, but if you find it, then you have an easy way. I don't expect you guys to remember from calculus how to do complicated limits. You don't have to apply L'Hopital's rule or anything like this. In fact, if there's any kind of non-trivial limit, like I would say this is a trivial limit, I expect you to be able to compute this, but anything non-trivial, I would, like, even in the homework, I put a note like, okay, if you need this limit, this is what it is. So I don't expect you guys to remember all your calculus or anything like that. Now this brings us now to little o. We haven't defined little o. So little o, remember the intuition was it's strictly less than. So the asymptotic growth, if f is little o of g, then f is growing strictly slower than g. And we will actually here we'll define it using a limit. So definition is that f equals to little o of g if limit, again, as n goes to infinity, of f of n over g of n equals to 0. Now you notice that if this is the case, then automatically by here, by here, we get that f is little o of g. So property, if f equals to little o of g, then f is also big O of g. And also f is not theta g, right? Because to be theta g, you'd have to be more than 0. And this is the opposite. This is when it's equal to 0. And if f is not theta g, that also means that f is not omega g, because theta means O and omega. So if you're O, if you're not theta, that means you're not omega. And this also kind of all makes sense if you think about if A is less than B, then A is less than or equal to B. A is not equal to B, right? So A is not, it's the equivalent of the theta. And A is not greater than or equal to B. All of this should make sense intuitively. Let's look at an example. We'll use something we already did. So we had looked at 6n and n squared, right? And we showed that 6n is big O of n squared. But really, this is very different than the case of 6n and n. 6n and n grow in the same way. So if I double the input size, both 6n and n double. Right? So the running time doubles if I double the input size. For these guys, for n squared and 6n, it's very different. If I double the input size, then this doubles, but this quadruples. So we want to separate these out, and that's what little o notation lets us do, is to say, actually, in this case, 6n is little o of n squared. Okay, so let's write that down. 6n is little o of n squared. This is, I'll call this a claim. And the proof, we apply the definition. So the limit of 6n over n squared equals to the limit of 6 over n. And again, this is a limit I expect you guys to be able to do. That's 0. And then that implies that 6n is big O of n squared. Excuse me, little o of n squared. All right, so we have all the definitions of the notation. So now I want to give you some properties about them and then show you how you can apply, like rules of thumbs that you can use so you don't have to redefine these things, reprove these things every time. Yeah. Yes, if f is little o of g, then that implies that f is big O of g. Yep. Just like a is less than b implies that a is less than or equal to b. Other questions? Okay, so there's some properties that I'll state. So one is reflexivity, which is that f is big O of f for all f. It's kind of trivial. It's like saying a is less than or equal to a for all a. For example, here you can say n squared is big O of n squared. Okay. Trivial, but we'll write it out anyways. Additivity says that if f and g are big O of h, then f plus g is also big O of h. So for example, n squared is big O of n squared, n is big O of n squared. So n squared is big O of n squared by reflexivity, and n is big O of n squared. I think, did we show that? We didn't show it, but for example, you can show it by saying limit of n over n squared. This is limit of 1 over n. This is 0. So that implies, I go to our properties, that the limit is not infinity, then f is big O of g. It's even stronger. It's actually little o of g. If it's 0, it's little o of g. But we don't need that for this example. So you take these two together, and now you can apply additivity to say n squared plus n is equal to O of n squared. Each of them is n squared, so the sum of them is big O of n squared. Then we have transitivity. So if f is big O of g, g is big O of h, then f is big O of h. For example, 6n is big O of n. We showed that n is big O of n squared. So 6n is big O of n squared. This I wrote out for big O notation, but the same thing holds for omega, theta, and little o. Okay, now with these kind of things in mind, we can get into the rules of thumb. The first one is that leading positive constants don't matter. For example, C G of n is theta of d times G of n for all constants. All constants, C, positive, I should say, constants, and D, and functions G. For example, 6n is theta of 8n. It doesn't matter what the constant is. You could put here 16 instead of 8, or you could put here 160, or you could put here 8 to the power of 100. Doesn't matter. These are in the same class, growth class. Next, polynomials are in a class according to their degree. So let me just remind you, polynomial, we can write, I don't know if you've seen it written like this, but you can write it if its degree is d, you can write it as a sum of ai n to the power of d. Let me give you an example. So if you're like 6n cubed plus 3n squared minus 2, okay, then a0, then this is, you can write as a3n cubed plus a2n squared plus a1n minus 2n to the 0. Here, when you think of it this way, then a3 equals 6, a2 equals to 0, a1 equals to 3, and a0 equals to negative 2. The degree of this polynomial is 3. So the property then is that P of n is theta of n to the d. Basically, the polynomials of degree d, it grows as n to the power of d. It doesn't matter, all this other stuff doesn't matter for the asymptotic notation. We just care about the biggest degree. Moreover, it's in a class by itself. So P of n is little o of nd plus epsilon for all epsilon greater than 0. So for example, n squared is big O of n cubed here, like epsilon equals 1. Or n cubed is big O of n to the 10. Here, epsilon is 7. So everything goes according to the degree. Root n, this is a polynomial too, right? It's not a polynomial, we can't write it in this form because it's not an integer coefficient, but it's still some power of n. So square root of n, remember this is n to the power of 1/2. This is big O of, for example, n. Oh, sorry, little o of n. All right. The base of logs It doesn't matter. That's another rule of thumb. And the reason is this. So if you remember, then you have this property from algebra. For all positive A and positive B, log base A of n is equal to log base B of n divided by log base B of A. So you can convert from one base to another, and you just have to scale by this log base B of A. That's just a constant. So we're scaling for example, log 8 of n equals to log base 2 of n divided by log base 8 of n, which is log base 2 of n divided by 3. Just scaling by a constant. So therefore, this is just theta log base B of n. Log base A of n is theta log base B of n for any B, for any A. And that's why you'll notice in homeworks and exams, I often don't write we don't even write the base of the log. Yeah. This one? Yeah, that's a theta. That's a theta. Yes. Yeah. I don't have the best handwriting, I'll admit that. You ask people that took this class with me earlier, I think my handwriting is improved. I practiced. Okay, now next rule of thumb is logs grow slower than polynomials. So what I mean by that is n to the power of d is little o of a to the power of n for all positive d and a greater than 1. So for example, n to the 100 is little o of 1.01 to the n. So on the left, you have a polynomial of degree 100, very big degree. On the right, you have an exponential function with a small base. Now, when something like this happens, you might intuitively think, well, like you plug in a few numbers and n to the 100 seems it's going to be a lot bigger than this guy. That's only up to a certain point. Because it's an exponential function, there's a point in which it overtakes the polynomial function. That point may be very far in the future. So, n to the 100 may go up like this, and the exponential may only overtake it at some point. But when it does, it then really goes off. So it's just about where that n naught is, but you still will always have that you still will always have that polynomials grow slower than exponential functions. This was a typo, so this should be polynomials grow slower than exponential functions. Now, back to the logs, let's show that they grow slower than polynomials. And it's a similar kind of logic. So log n is equal to little o of n to the d for all not positive d, for all d greater than 0. For example, log of n is little o of n, like square root of n. So we got kind of initially we got logs, log functions, then we got polynomials, then we got exponential functions. So let me show you this again so you have a intuition. So here's your, this is not showing a log, but here you have a polynomial, varies degree, and here you have exponential functions. And exponential functions can also be differentiated by their base. So let's see. Exponential functions grow according to their base. So what I mean is for all a less than b, have that a to the n is little o of b to the n. Right, so for example, 1.5 to the n is little o of 2 to the n. So this constant matters, but it's not because it's not a leading constant. It's a constant inside the exponent. It's the base of the exponent. That's really crucial. You can see that here, right? If you compare this column to this one, you could see there's big differences. So here, like 11 for n equals 50, you have a difference between 11 minutes and 36 years. One more thing I want to show you is about polylogs. And to do that, I need to give you another property called the multiplicative property. So if you have a function that's big O, so f big O of some h1, some function h1, g is little o of h2, then f of n times g of n is little o of h1 of n times h2 of n. Let's see that with an example. So for example, here we have this n log n, and you see here it's squished between n and n squared. And you can see there's a difference. So like for large inputs, 1 second, 20 seconds, and 12 days. So this seems to be in a class by its own, and let's see how we can derive that. So n, n, for example, n is big O of n squared. Big O of n. That's just reflexivity. That's why we needed this kind of property, just to be able to make statements like this. And then log n is equal to little o of n. We show that, we saw that at rule of thumb, logs grow slower than polynomials. So n times log n is now little o. So n times log n, we have little o of these two guys, so little o of n squared. Little o of n squared. Now I can tell you something about functions that are polynomial and log. So what about like log n squared? Okay, so let's polylogs grow slower than polynomials. So what I mean here, we're going to use some notation. So instead of writing log n to the power of d, we will write log, we'll put the d here. And this is just equivalent. This is, so I'm going to use this notation. This just means that it's like an equal sign, but it's saying it's not equality, like it's not an algebraic derivation. I'm just saying I'm defining this notation. What's on the left is a notation that I'm defining, and this is what it's going to be. All right, so all I'm saying is we'll put the d here. It means the same thing. Just a different way of writing it to save space on the parentheses. I think the book uses it, so I want to make sure you guys are aware of it. Property now is that log d n is little o of n to the a for all positive d, or a d greater than 1, and positive a. To prove this, you can use multiplication. In the interest of time, I'll skip it. Guys, any questions? Yeah. Yeah. So use multiplication property, what I mean. So with this, we just multiplicative, let me write this better. Multiplicative property, I'll write it out. So yeah. Use, no, the proof is omitted. I'm not going to write out the proof, but I'm giving you a hint. Multiplicative property. Proof. Yeah. Yeah. Yeah, it's small o. So these guys are, this is small o, small o, small o. This is a big O. This is a big O. Other questions? How many of you guys are kind of comfortable, semi-comfortable with this notation? Okay, not a lot of you. So ask me questions. We have time. I will explain more. Yeah. Well, so think about how you would try to characterize this. Like n log n, where does it belong in that rating? So you have multiplying two functions. So one is a polynomial, n. You know what to do with n. N is theta n. We looked a lot at n. Log n, we know that logs grow smaller, slower than polynomials. So log n grows slower than n. Now, I want to put those facts together. So I'm multiplying a function n by some other function that's growing slower than n. So I want to say that I'm getting something that's slower than n times n. All right, so I want to be able to say this, get this little o of n squared. Like normally, I can't just say it. So that's why this multiplicative property allows me to say that. It says, if I'm multiplying two functions, f of n, g of n, and I know that the first function is, we have a big O bound for it. The second one, we have this, not big O, but little o, so it's strictly smaller than some function. Then the result of multiplying it, we get something that's strictly smaller than multiplying H1 and H2, the two bounding guys for f of g. This is the motivation for this guy. All right, I'm going to go through. Wait, how many of you are pretty comfortable with this leading positive constants don't matter? All right. How many of you are pretty comfortable with polynomials in a class grow according to their degree? Okay, we're starting to lose people. How many are comfortable with this? Logs based don't matter. Okay, that's most of you. How many of you are comfortable with this? Polynomials grow slower than exponential functions. Okay, that was good. Logs grow slower than polynomials. Row. Exponential functions grow according to their base. Okay, so we come back. Polynomials in the class, no, which one do we have trouble with? Yeah, polynomials in the class according to their degree. Okay, so this one you guys had trouble with. So how many of you get this notation? Okay, so maybe I'll explain this. Okay, good. Look, writing P of n equals this. This is a polynomial function, right? You guys intuitively see that, right? How do I formalize what a polynomial function is? Well, you got some degree. So the degree is just the largest value here in the exponent. So here the degree is 3. Now I got terms. I got an n cubed term, an n squared term, an n term, which is nothing in this case, and n to the power of 0 term, right? This is, I can write here, this is n to the power of 0. Just 1. So I can abstract it by writing it like this. So I got some n cubed times a coefficient a3. So in this case, this coefficient is 6. Then I got n squared, 3n squared, which is n squared times this coefficient a2. And a2, oh, here's a mistake. A2 is 3. Then I got a1 times n. And here there's no n term. So a1 is just 0. Finally, I got this n to the 0 term with coefficient a0. Oops. a0. And a0 in this example is -2. So these are my coefficients. Now I can write P of n in this form. So the sum of I through d, so the sum of I going through 0 to d of ai times n to the power of d, right? So a0 times n0 plus a1 times n to the power of 1, a2 times n squared plus a3 times n cubed. I can write it like this, at least when I have integers as the powers. How many of you are comfortable with this definition of P of a polynomial? Yes, all right. So why is that important? Because I want to be able, I wanted you to understand how we can write a polynomial. We'll see it in a homework assignment possibly. And now, how does this polynomial grow? What's the rate? Well, it's this is the rule of thumb. It's growing according to its degree. So this, for example, this polynomial is theta of n cubed. I just look at the degree, the biggest power, and that's what the rule of thumb says. I got a complicated polynomial. I don't care about this stuff. I don't care about this stuff. I just care about the leading power. If you go back to the start of the class, this guy, I'm just going to write this as theta n squared. The other thing I'm writing here is that that class is just like n squared is the class of all polynomials, degree 2. N cubed is a separate class. So, so n squared is not just big O of n cubed, it's actually little o of n cubed. Polynomials grow according to their degree. So if you increase the degree, now you've got something that's growing faster, strictly faster. Okay. How many of you are comfortable with this? All right. Good. We have some time. Yeah, question. Yeah, let's talk about additivity. Additivity. So I want to prove what is n squared plus n. Like, how does it grow? Actually, now that you've seen the polynomials property, you can say this is a polynomial of degree 2, and it grows as n squared. But let's forget about that for a second, so we can do it another way. I've got a sum of 2 functions, and I know the behavior of each function. So n squared, I know is O of n squared, and n as I also know is O of n squared. So all this additivity property is saying is if I sum 2 functions that are O of n squared, the result is also O of n squared. That's all. Now, some useful identities. This is just going to be some algebra, but it's going to come up. So first of all, you guys, is this an exponential function? How many of you think it's an exponential function? How many of you think it's a linear function? Okay, so if it's a linear function, it's n. This is just the property of logs. General property of logs is, write it, that sum a log base a of n equals to n. Like if you think about this, what is log base 2 of n? It's, you need to raise 2 to this power to get n. So if you now take 2 and raise it to that power, you get n. That's true for any log, for any base. Now, it could be that the base of the log is different. So what if you get like 9 log base 3 of n? How many of you think it's an exponential function? How many of you think it's a linear function? How many of you think it's a quadratic function? Okay, so the property here, so the property is that well, yeah, so the property states that a to the log base b of n is equal to n to the log base b of a. So in this case, this is the property n to the log base 3 of 9 equals to n squared. you're curious, this I can write as 9 is 3 squared, right? So I can write it like this. Log base 3, which I can write 3 log base 3n squared, which is now applying the first property, n squared. So if you're just curious for the intuition behind that. Log of n factorial, you might see that come up. That's theta n log n. We're not going to derive that. That's slightly more complicated. That's using Stirling's formula. You guys, have any of you have seen Stirling's formula for factorial? Most of you have not. So, just think of this as a property you can use when you see factorials. We might see n choose 2, for example. Now, n choose 2, remember, is n times n minus 1 over 2. This is n squared over 2 minus n over 2. This is a polynomial, folks. Polynomial of degree 2, theta n squared. It just has non-integer coefficients, which is totally fine. Right, so the property is n choose 2 is equal to theta n squared. You might have seen, well, I bet you've seen this sum. Remember, this is equal to n over n plus 1 over 2. And this is again a polynomial of degree 2. Right, so that's a property. And you probably have seen this, but you've probably forgotten the formula for it. How many of you have seen this somewhere? Yeah, so you guys have seen it. I don't remember the formula. I always look it up when I need it. It's like this. What's this? This is a polynomial. If you write out all the terms, you'll just get, the biggest power will be 3. You'll get n cubed. And a smaller power. So this is going to be theta n cubed. So that might come up. Finally, you might see geometric series. The geometric series is, for example, 0.5 plus 0.5 n plus 0.5 n squared. Oh, sorry, to the power of 2 to the power of 3 plus 0.5 to the power of n. This is a type of geometric series, or you might have, this is maybe silly, but 1 plus 1 squared plus 1 cubed plus 1 to the power of n, or 2 plus 2 squared plus 2 cubed plus 2 to the power of n. Now, in general, you can write g of n is equal to a sum. There are terms from going from 0 to n, and each term is c to the power of I. So here, c equals to 2. Here, c equals to 1. Here, c equals to 0.5. So this is called the geometric series. When you see a geometric series, you can use this nice property about its asymptotic behavior. So write this out, theorem. So you have what g of n is. If c is less than 1, then g of n is theta 1. If c equals to 1, then g of n is equal to theta n. And if c is greater than 1, then g of n is equal to theta c to the n. All right, we're not going to do the proof of it, but I just want to give you some intuition. So probably the easiest is this case. C equals 1, then you're just summing a bunch of ones. Actually, you're summing n ones. So that's just n, and it's clearly theta n. When you're summing, if C is less than 1, notice that each of these terms is getting smaller and smaller and smaller. And in the end, what you get, theta 1, what is theta 1? It's a function that doesn't depend on n. It's theta 1 is another way of saying it's a constant. And what about C more than 1? Actually, you guys have seen this with 2. So you probably have seen this sum of the powers of 2. If you sum all the way up to 2 to the power of n, you get 2 to the power of n plus 1. This is, if you count the number of leaves in a binary tree, you use this formula. In that case, the series goes as a function of that last term, of the biggest term, c to the power of n. Okay. So you can use these on your homeworks and exams. The homework will be posted within an hour.